Aice Physics Motion Test Question 1. A cannon fires a cannonball with an initial speed v at an angle alpha to the horizontal. Which equation is correct for the maximum height h reached? To find the maximum height h, we need to consider this trajectory up to here. So as the cannonball rises, what happened to the horizontal and vertical components of this initial velocity? I'm going to hypothetically imagine the cannonball is right here. And also, what will be the components of the velocity when the cannonball is at the maximum height? So let's start from the beginning. Let's go back here where the cannonball was initially launched. Because this velocity is an angle, we are going to have a horizontal and vertical component. So this here is VH and this is VV, vertical velocity. At this point, at this location, the cannonball will have the same, let me try to measure here like 2 centimeters. It will be the same horizontal velocity, will not be affected by gravity. However, VV is going to be less. The vertical velocity will decrease over time, and the horizontal velocity will not be affected. Now, at the maximum height, what is going to happen is this vertical velocity is 0. So there is no component here. However, there is a horizontal component that remains constant during the entire trajectory. At the maximum height, h, the vertical component is 0. My second bullet here is how to write the components in terms of this angle. From your notes, here we have the horizontal component is this initial velocity times cosine of this angle, and the vertical velocity is the initial velocity times the sine of this angle. Now we need to find an equation that relates the height and this velocity. So what we are going to do is using one of these equations. We don't have any information here related to time, so I'm going to try to get an equation that I have the height, which in this case is d, and I have the initial velocity, which is this one. I'm going to use equation 3. My final velocity right here at the maximum height is 0. All this here is on the vertical view, no horizontal, vertical. So here is 0. My VI is this, V sine of alpha square plus 2. The A, the acceleration, is acceleration of gravity, G. And D is the maximum height, which is H. Now I'm going to rearrange this formula in terms of H. Before we arrange this equation in terms of H, let me look if the acceleration of gravity sign is correct. Because here is my G, because the cannonball is going up and the speed is decreasing, which means it's decelerating. So because it's decelerating, we are going to change this sign plus with minus g. So minus g. Now I'm going to flip this a little bit and rearrange all this. So you'll be negative 2gh is equal to negative v sine of alpha squared. So because both sides are negative, so that will be positive now. And my h is v sine of alpha squared over 2g. And yes, I do have an answer, which is C. Question number 3. The variation with time t of the velocity v of an object is shown in figure 1.1. Determine the acceleration of the object from time t equals 0 to 4. This is not part of the question, but I would like to explain each segment here. Segment A, B, and C in terms of the velocity. This is not part of this question, but I would like to take this opportunity to explain the transition for the velocity time graph on this section A, B, and C. Section A indicates at time 0, the object starts with an initial velocity, which is 0.75 meters per second, and this straight line indicates that the object accelerates at constant acceleration. And so that's why showing here the increase of the velocity at a constant rate. At section B, it indicates that from 4 to 8 seconds, the object is moving with the same speed because it is a horizontal line, which indicates the acceleration is 0. There is no change in velocity. At section C, the object is decelerating and with a constant deceleration, which means that the velocity is decreasing over time with the same ratio. And right here, after 12 seconds, so the velocity is 0. In summary, accelerating, not accelerating, and decelerating. The question is asking the acceleration from 0 to 4 seconds. The definition for acceleration is the rate of change in velocity. In terms of a formula, is the change in velocity over change of time, which means is the final velocity minus initial and final time minus initial time. So the sub F here indicates final and I indicates for initial. So let's look at the velocity. The final velocity here is at this location. You just now need to read the squares. To calculate the value of each square, one thing that we can do here is look the difference between 1.5 meters per second minus 1.25 meters per second. So in this interval, I have 1, 2, 3, 4, 5 boxes. So how much is each box in meters per second? Okay, so this difference here is 0.25 meters per second, corresponds to 5 boxes, which means that one box is 0.25 meters per second over 5. So each box on the y direction corresponds to 0.05 meters per second. So I have here 1, 2, 3 boxes. Each box is 0.05 meters per second. So 3 times 0.05 is 0.15. So all that I need to do is add 0.15 to 1.25. So plus 1.25 is 1.4. So this intersection corresponds to 1.4 meters per second. Even though this type of problems, they're pretty simple, is information is straight from a graph. A great source of error is that students sometimes they are too quick to determine the value of the box. So they don't go through a process of be very accurate and collect the wrong numbers from the graph. So my final velocity here at 4 seconds is 1.4 meters per second minus the initial is 0.7. Wait a minute, look at this. This is 0.75 is here, so one box is 0.05, right? So that will be 0.75 minus 0.05. So this intersection here is 0.7 over time. So it's from 4 to 0. So 4 minus 0. So that gives us an acceleration of 0.175 meters per second square. Make sure that you square second. Or in Cambridge format, it will be 175 ms minus 2. Question 4. Which graph shows a variation with time t of the velocity v of an object falling vertically downwards in a vacuum? So let's see what happened with a vertical motion of an object falling vertically downwards. So let's say this is time 0 when this motion starts, and the initial velocity here is 0. After 1 second, because this object is falling with acceleration of gravity, which is 9.81 meters per second every second, which means 1 second passes by, and then the velocity here now is 9.81 meters per second. And so on. So 2 seconds, then you'll be 2 times 9.81 meters per second. Now I have a velocity almost equal to 20 meters per second, which is 19.62 to be exact. So, and then 1 more second passed by. Now I am in 3 seconds, so the velocity is even higher. In conclusion, in this motion, we have a constant acceleration, which is 9.8 meters per second square, right here. And the velocity is increasing over time. So what would be the behavior of a velocity time graph? Option A, the velocity here is decreasing over time as the time goes by. So the velocity here is less, and less. Option A is not correct. Option B indicates that the acceleration is not constant because it's a curve. So this is a curve. This is a curved line. Indicates the acceleration is not constant. So this is incorrect because acceleration is constant. The acceleration acting on the object here is not constant because it's a curved line. So this is also not true. I know by elimination will be option D, but here indicates that it starts from 0, which is correct. Time 0 is 0, and the velocity is increasing over time, and the straight line here indicates that acceleration is constant because it's a straight line. Question 6. A cyclist pedals along a race horizontal track. At the end of the track, he travels horizontally into the air and onto a track that is vertically 2 meters lower. The cyclist travels a horizontal distance of 6 meters in the air. Air resistance is negligible. What is the horizontal velocity v of the cyclist at the end of the highest track? So this motion is related to horizontal launch. So right here we have the cyclist will have a horizontal velocity throughout the trajectory up to when lands on the horizontal track here, and the vertical velocity initially is 0 and is going to accelerate over time. So in this case, I'm going to use the two tables, one for the horizontal direction and the other one for the vertical direction. This way, I can calculate the velocity of the cyclist once he left the highest track. So here is a table for the horizontal, and here is a table for vertical downward, because that's what is going on. So horizontally, let me call VI and VF the same value, because is horizontally the velocity is the same. So I'm going to call here VH for horizontal, VH for horizontal. The distance, the horizontal distance is this, is 6 meters. The acceleration is 0. Why? Because the velocity didn't change. It remains the same. And let me call the horizontal time TH, the time that takes horizontally for the cyclist hit the lower track. Now vertically downward, the initial velocity here is 0. The final velocity, we will need to calculate, I don't know. It's going to arrive with a final velocity. It's not 0 here. And the highest, the distance vertically, here we have 2 meters, which is this. So vertically, we need to look everything in this direction. Acceleration, so is accelerating downwards. So the acceleration of gravity is 9.821 meters per second square. Positive because the velocity is increasing over time. And let me call this time vertically TV. Okay, so now that we have this information based on the story, I need to select the right equation for each type of direction. So here we have 4 equations. Equation 1, 2, and 3. Acceleration is not 0, so we have acceleration. Equation 4, acceleration is 0. So in this case, I'm going to write this equation right here for the horizontal table because acceleration is 0. So here we have VH is equal DH over TH. Perfect. I do have DH, which is this. This is DH. But I do not have the time. But there is a trick here. In this type of motion, the horizontal time and the vertical time are the same. So what I'm going to do is calculate the vertical time using the vertical information. So let's see which equation will be the best for the vertical distance, vertical direction actually. So we are looking for time. So we need to select a formula with time. So this is not a good option. We don't have time here. So we are between this and this. The first equation, I don't have the final velocity. I will have to calculate. So let's see if I can find something that, with the information that I already have, that can lead me to the answer. So the second equation I could use, because I know my VI here is 0, and then I will have just this section of this equation, and I can calculate the time, the vertical time. Okay, so this is the second equation. My VI here is 0, so this is 0. So what I have left is D is equal half AT squared. My D is 2, half. My A is 9.81 meters per second, and T is square V. So this is 2, half of 9.8 is 4.9, TV square. So TV square is 2 over 4.9, and doing square root, so this square can disappear. So this is equal to 0.64 seconds. That's the value of my TV. So here TV is 0.64 seconds, and because TV and TH is the same, so now I can use this information. My DA here is 6, and my time is this. So the velocity the cyclist is going to leave this higher track is 9.39 meters per second. So this is the final answer, and this is the option B. Question 8. An astronaut on the moon where there is no air resistance throws a ball. The ball's initial velocity has a vertical component of 8 meters per second and a horizontal component of 4 meters per second as shown. The acceleration of free fall on the moon is 1.62 meters per second square. What will be the speed of the ball 9 seconds after being thrown? So the question is asking what is the speed of the ball after 9 seconds. So 9 seconds, let's imagine, we don't know what is 9 seconds is. So let's assume that 9 seconds is right here. And what happened is, how will be the components of these initial velocity? So initially, horizontal is 4. After 9 seconds, you also be 4. Will not change. Horizontal velocity is not affected by gravity, so keeps the same value. Now, vertically, we expect be less because is decelerating, is going up. So let's say that we assume that is going. Let's see. Let's try this way. See if it works. So my let's say this is my VV that I don't know the value, and this time here is 9 seconds. Assuming that is in that location. I don't know. I'm just throwing, think that could be here. Could be 9 seconds, could be over here. I don't know. So let's try this way first. Doesn't work. I will try a little bit farther on the other side. So let me set up a vertical table after 9 seconds. I'm not doing horizontal because, like I said, horizontal is the same unless I feel like that I need more information. So let me start with this. We need to start from something. So VI, VF, DAT. So my initial velocity from here to here, right? So initial velocity here vertically is 8 meters per second. My final velocity here, I don't know. That's what I'm trying to figure out. My vertical distance, I also don't know. So let me call D. I don't know. The acceleration I do know is decelerating. So is decelerating, I know this because it starts with a velocity and is going to get less and less and less as going up. So we are on the moon, not on Earth. So you need to pay attention on that. So it's 1.62 meters per second square. However, negative because it's decelerating the way that I set up. And the time here, 9 seconds. So let me look my options here. I don't have distance, so I'm not gonna use 2 or 3. I do not have distance. And I'm not gonna use 4 because it is acceleration. So what is left is this one. So let me use this one by elimination. Equation 1. Okay, doing the substitution, this is what I'm looking for. VV for 9, let me call final right here. The initial is 8. Acceleration is negative 6.2 and time is 9. I think it's gonna work. So VVF is is 8 minus 1.62 times 9, negative number, 6.58 meters per second. This is not the final answer yet, because it's not asking the vertical component. It's asking this V right here. So I will have to do some changes. So this negative indicates that this vector is not up, it's down. So this vertical velocity here is negative, so this vector is down, and the horizontal is all the time in the same direction. So I'm going to calculate my velocity at 9 seconds when I have these values. So this is how it works. So you are going to close this rectangle. You are going to draw this like this. So this is your vector V that you want to calculate. And here we are going to move in this direction, 6.58 meters per second. Okay, so now what we are gonna do is, okay, I move this to the other side. So this is the right triangle. So I'm going to calculate the value of V, use Pythagoras theorem. So V squared is 4 squared plus 6.58 squared. So V squared is, okay, not that, because I already calculate here. That's the value. The final answer is this. V is 7.7 meters per second, which is option B. Question 9. A stone is thrown vertically upwards. A student plots the variation with time of its velocity. What is the vertical displacement of the stone from its starting point after 5 seconds? Every time, every time you have a velocity time graph, you can calculate distance or displacement or both using the area under the line graph. Because it's asking displacement, you need to consider the sign of the area. If it was distance, you just add all the areas regardless of the sign. You just add them. But because it's asking displacement, so you need to be careful. So let's see how we're gonna do it. First, where is 5 seconds? 5 seconds right here. So it's asking the displacement from 0 to 5. So from 0 to 5, you have two areas. The shape of both areas is a right triangle. So area 1, the base here is 3 times height, which is 30, divided by 2. So this is 45 meters. Area 2, same, base times height divided by 2. So base here is 2 times the height is negative 20 divided by 2. So this is equal to minus 20. Now the total area is equal to A1 plus A2. And because it's displacement, you need to consider the sign. If it was distance, and then you add both. Because displacement, you cannot. So it will be 45 meters minus 20 meters is equal to 25 meters. So answer B. Easy question. Question 11. A car is traveling at constant velocity. At time t0, the driver of the car sees an obstacle in the road and then brakes to a halt. The graph shows the variation with time of the velocity of the car. How far does the car travel in the 5 seconds after the driver sees the obstacle? So in this case, it's not defining the time that happens. So this is what's going on. So we have two transitions here for velocity time graph. So let's call this A transition and this is B transition. So at A transition, the car is traveling at 20 meters per second, constant speed, acceleration 0. In this case here, from 0.8 seconds to 5, so obviously this car is decelerating. So is the velocity decreases over time and the deceleration value is constant. So here is asking to find how far travels from when see the obstacle. So it's going to see the obstacle right here at 0.8 seconds, obviously, and right here is the area that we are looking at, this area right here. So this area is base times height divided by 2. The base here is 5 minus 0.8. Height is 20 divided by 2, and this is 42 meters. Question 12. I want to encourage you to read this question, but if you are watching the same video, this is the same as question 4. So review question 4 and you can easily determine which is the right answer for this question. Question 13. A projectile is launched at point O and follows the path OPQRS as shown. A resistance may be neglected. Which statement is true for the projectile when it is at the highest point Q of its path? So I'm going to first eliminate question C and question D because at this point I have not explained to you about kinetic energy and momentum. So those two answers are not going to be applied for this question anyway. So we are between just A and B. A, the horizontal component of this projectile's acceleration is 0. This is true. And the horizontal component of the projectile's velocity is 0. This is false. So that's the answer. Question 14. A stone is thrown upwards from the top of a cliff. After reaching its maximum height, it falls past the cliff top and into the sea. The graph shows how the vertical velocity v of the stone varies with time t after being thrown upwards. R and S are the magnitudes of the areas of the two triangles. What is the height of the cliff top above the sea? Let me translate this story into a diagram. So here is the cliff. And below here we have the sea. The ball is being thrown upward. So that's the trajectory. It's going to stop right here, and now it's going to fall down. Falls, falls, and is going to do the splash here on the surface of the sea. So here we have, when the ball comes down, it's going to pass again through the cliff top, right here. So the problem here is asking the height of this from the top of the cliff to the surface of the sea. What is this height? And once that the height be determined based on this graph and based on a area of this graph expressions. I'm going to analyze this diagram with the graph. So the ball is thrown upwards with initial velocity, vi, and then go all the way up and stops, is 0. So this looks like this S because it starts with initial velocity and ends with 0. So this here going up is my S area. Then going down, it starts right here with 0 up to about the same value that the stone had when was initially thrown from the top of the cliff. So right here will be about the same. I'm going to use my ruler and try to figure out how much will be this. So this is about this much before 2 marks here, and this will be 2 marks here. So this. So look what happens. This here is my S as well. However, after this reaches the back to the cliff top again, keep falling to the sea. So from here, from 0, keep falling. The whole thing here is my R. So from 0 to here is my R, all this bigger triangle. Now, because we have the same values here, which S and S here, S and S, and this part right here is from the cliff top to the sea. So let me look at the options. The height of the cliff top is R. No, it's not, because this is not R. R is the entire thing. When the stone stops in the air and starts to come down. So this is not correct. So the height of the cliff top to the sea is S. No, it's not. So S is just this portion right here. So this is incorrect. Is R plus S? R plus S. No, that would be too much. That's not the right answer. The last one is R minus S. I would say it would be easier to answer this question looking at the diagram that I did based on this graph. So if you look at this diagram, the height of the cliff is the R minus S, that you give the height of the cliff. And I did the diagram based on this graph. So this is the right answer. Question 15. A ball is released from rest above a horizontal surface. The graph shows a variation with time of its velocity. Looks like a bouncing ball here because it's first impact, second impact, third impact, and it's kind of losing velocity as hit the ground. So here says that areas X and Y are equal. This is because, so I'm going to read sentence by sentence and try to figure out which one is the correct. So before I do this, let me determine one thing. We know in a velocity time graph, the area under the line or the shaded area, the area is equal to the distance or displacement. So in this case, we can see that X and Y is equal. So the distance is the same. So to narrow things down, because those sentences are pretty long, to narrow things down, when you read each sentence, we need to find anything related to distance, because that's what the X and Y area is about. So area is equal to distance. Not acceleration, not time, not velocity, is distance. Okay, so the first one says the ball acceleration is the same during its upward and downward motion. Going upward, the acceleration is going to be negative, and downward is going to be positive, which means the ball here is going to decelerate and here is going to accelerate. Even though the acceleration has the same value, let's say if it's happening with vertical motion, let's say the acceleration here is 9.81 meters per second square. Even though it's the same value, but the fact that sometimes it's positive, sometimes it's negative, is changing the whole results. So we cannot state that acceleration is the same. It's the same magnitude, but it's not the same direction. So we cannot say this is a correct sentence, so this is false. And another one that I want to add to option A is acceleration is nothing to do if the area is X and Y. B, the speed at which the ball leaves the surface after an impact is equal to the speed at which it returns to the surface for the next impact. Even though sounds correct, but is not related to the area being equal. So this one, I will put in a hold until I find something better. C, for one impact, the speed at which the ball hits the surface equals the speed at which it leaves the surface. So here the speed the ball hits the surface, so the first impact, the speed here is higher than the speed that leaves the surface. So I will say this is not correct. And D says the ball rises and falls through the same distance between impacts. Yes, the ball rises and falls through the same distance. X and Y is related to the area under the line, which is distance. So this is true. So the answer is D.